So I'm really excited to share this project that I've been working on for the past couple of years. Actually, I started working on it in Israel, and when I started off my career, I really wasn't that into technology. I was more kind of on the design side of the spectrum, very creative, drawing, and so I thought I would go to architecture school and become an architect, and I did that. And kind of as I was working there, I realized that I'm actually more excited about technology, and I love all the cool things you can build with technology, and so that kind of catapulted me into working on more technology-oriented projects. And this project of houses on Mars actually started when I was an undergrad in architecture school, and my research thesis was about building houses on Mars and the urbanization of Mars, but it was very theoretical, it was very design-oriented of, what could our future look like on Mars. And then as I was working on that project, there just happened to be an open call for proposals at NASA for proposals for 3D printed Mars habitats. And I thought to myself, well, I've been thinking about this for a while. So I called up my friend Lior, who had a 3D printing startup. And I said, hey, Lior, there's this NASA competition. Let's submit a proposal. And he's like, well, it's only a 2-pager. We could do that over the weekend. So we sent in our 2-pager to NASA, and they liked it. And then they said, okay, send in 5 pages, send in 10 pages, come to New York with your 3D printed model. And we still had no idea kind of who was in this competition. And then we show up in New York, and we realize that actually they only invited 30 teams to New York out of 163 that started out. And that the other teams there weren't student teams, that they were Pritzker Prize winning architects and teams of PhD scientists from MIT. We said, oh, wow, this is really cool. And then the other thing we realized when we were there was that actually our proposal was very different from everybody else who had sent very highly kind of technical reports in some way. And we submitted a comic book to NASA. Granted, it was a technical comic book, but this was kind of our initial proposal. And so our first thought about kind of how we wanted to build these Mars habitats was to bring a high-performance inflatable structure that had like a double and triple skin. And because of the difference in atmospheric pressure on Mars, you could inflate it conceptually relatively easily. And then we wanted to fill that with solar sintered sand. So basically taking sand and kind of melting it to create a more structural material and filling it with that, and then have kind of sintering robots that were going around on Mars sintering these bricks and then working like swarm robotics. So basically working collaboratively to build a dome to protect the habitat from radiation and from micrometeorites. So that was kind of the initial concept. And we said, oh, we're going to have like multiple little sintering robots, because if one dies, you have redundancy. So that was kind of where we started out with the initial phase, and this was the design phase. So we got to New York, and we saw who we were competing against, and we actually won an honorable mention in the first stage, which was awesome. We beat the team from MIT, so that was exciting. Me and Lior with our... Thank you. With our project that we did literally in the basement of his mom's house. So that was fun. But then the next phase of the competition was actually to like build something and to print something and to send it to NASA. And we still had no budget and no idea what we were doing. But we said, and so we kind of put the project aside. I graduated. I went then to manage a tech fund for the city of Jerusalem. So I was doing economic development policy. Lior went back to his startup. And then through that tech fund, I met this professor and researcher who specialized in developing new materials for 3D printers. And the next phase of this NASA competition was to come up with a new material that's based on materials that can be found on Mars, so Mars regolith simulant, and to come up with a new material to 3D print it. So I talked to this researcher, Michael, and I said, hey, Michael, there's this competition, this NASA thing. We weren't thinking of going to the next phase in it, but it's kind of in your field of expertise. What do you think? Are you interested? So again, NASA documents, it's like 50-page document. He takes it, he reads it over the weekend, and he gets back to me, and he's like, Helen, you know that the deadline for this is in 6 weeks, right? And I'm like, yeah, that's plenty of time. It's like in architecture competitions, you spend maybe 2-3 weeks working on something. Well, apparently not in material science. You spend like a year or 2 years making a new material. So Michal's like, but you know, Helen, you're really lucky because this is extremely close to a field of research that I'm working on. I think I have something that can work for you guys. Get me some Mars dust so we can try it out. Again, Israel, we did this in Israel. It's a small country. There's like 2 Martian geologists in the country, so I call one of them up, say, hey, Roey, where can I get some Mars regolith simulant, aka Mars dust? Roey, where can I get some Mars dust? And he's like, well, Helen, you can either order it from NASA. It's a JC1 something something, but it's going to take 3 weeks to get here, and it's going to cost you. Or you can just go to the quarries in the north of Israel and pick up crushed basalt rock from there because it's very similar. Go to these 3 quarries and bring me back some samples, and I'll tell you which one's the best. So we went with buckets it went back to sleep. We went with buckets and with our cars up to a quarry in the north of Israel, and we collected fake Mars dust, which we then brought back to him to the lab to simulate, and to test. See, there you can see me. We're collecting Mars dust from different quarries in Israel. Sorry, it jumped quite a lot. There we go. Again, still 0 budget, so we were going to use the printer in Michael's lab, but then about 2 weeks before the deadline, we broke his printer, and replacement parts take 3 weeks to get. So I said, well, if we can't use that printer, let's try and borrow a printer. So I called kind of everyone in Israel who had a printer that might be relevant and then say, hey, we're doing this cool Mars project, can we borrow your printer? And I found out that people don't want to loan you their $1 million printers to put weird materials in that are going to void the warranty. So then I said, okay, well, that's not working. There's about 10 relevant printers in the country, and I talked to everybody who owns one. So if we can't buy one and we can't borrow one, then let's build one. So 2 weeks before the deadline, we're trying to kind of build a 3D printer. Again, we have 0 budget for this project. So we're kind of borrowing pieces and trying to figure out like what that's going to look like. So here you can see this is a like $150,000 robotic arm. We convinced the guy who imports these arms to in Israel to like let us borrow his robotic arm and use it in the showroom. And that provides the movement function of the 3D printer, but we were still missing the extrusion function, which is basically like what pushes the material out. And so we were looking for like these clay-based extruders. They're pretty expensive. Nobody had one to loan us. But we realized that actually the function is kind of similar to what a pasta machine does. And so what you see here is actually a pasta machine that we adapted. And here we attached like a pasta machine to the end of this robotic arm and basically like 3D printed adapters and fed our Mars dust recipe into this pasta machine. Thank you. Yeah, it was so crazy. But the craziest thing is that it actually worked. So we were able to 3D print the cylinder. As you can see in some of the pictures, actually maybe not, you can see that the resolution wasn't amazing, right? It's not super straight and accurate because, well, we used a pasta machine. But it performed really well in structural tests, significantly past the NASA required minimum, so that was awesome. So we're really happy that worked. And so then in the next phase of the competition, we had to print something bigger. And at this point, I'm like, okay, well, this isn't going to fit in the tank of the pasta machine, so we're going to need some funding. And again, I kind of worked in the VC industry before. People are not jumping up and down to fund 3D printed Mars habitats. You know, there's not a clear business model to that. So that was challenging. So then I thought, well, where can I find people who might want to fund this kind of cool, crazy project? So I said, International Space University. I'll meet other people who are excited about space stuff. So I went to International Space University last summer and kind of trying to raise money. And I see the deadline is getting closer and closer and closer, and we still don't have money, and we still don't have clay-based extruders, and we still don't have a printer. So at some point, I'm kind of in Ireland at Space University, and I call up the director of the Israeli Space Agency on his personal cell phone, and I may or may not have confused the time zones and woken him up, but I call him and I say, "Hi, Avi, it's Helen, the crazy girl who wants to print houses on Mars. Remember me?" He's like, "Yeah, Helen, it's hard to forget." What can I help you with? So I said, "Avi, remember the competition we're working on? If we don't have like $5,000 in the next 3 days to buy like 60 liters of material, you're not going to have an Israeli team in the competition anymore." So he said, "Okay, Helen, let me see what I can do." Also, $5,000 is like the magic number. Above that, it's like government tender. Under that, it's not government tender. So I said, "Avi, maybe you can find us some money." He said, "Well, we can't do it so fast from a government agency, but I'll make some phone calls." So he found us basically a well-funded startup that was excited about the project and was willing to donate the materials to us. The next morning, I called the guy, and he's like, "Yeah, this is really exciting. I'll buy you your materials." So that was amazing. So then we had our materials. So like, okay, well, we have the kind of the material. Now we have to just get all these other things like the printer and the extruder. So at this point, there was another investor who said he was willing to match funding. So I called him and I said, "Hey, Michael, so we didn't exactly raise more money, but this guy is buying us materials. Will you match the funding?" And he's like, "Yeah, I'm literally sitting on a plane on my way to Africa. I'm going to be off the grid for like 3 weeks, but I'm in." So he sent us an email, and we're like, "Okay, we'll figure it out when you get back." And then we're in this kind of crazy scramble to get all of these parts in time to actually have it so we could print something to have it in time for the deadline. So then this was a really good lesson for me in operations and in sourcing parts for hardware. So we finally wanted these amazing clay-based extruders, this company called Wasp in Italy. So I call them up and I'm PayPaling you the money today. How fast can you ship it? And she's like, "Oh no, we have to make them." I'm like, "What do you mean? It's listed on your website." She's like, "Yeah, once you pay, we make them. It'll take us like 2 weeks." I'm like, "No, you don't understand. I don't have 2 weeks." So then we called the engineers and spoke to them in Italian and basically convinced the engineering department they could do it faster. And then called back sales and we're like, "So we talked to your engineers and they can do it faster." Yeah, I'm sure they love me there. Then we did that. And then we agreed instead of 2 weeks that they could do it in 2.5 days. And then about a day and a half in, I called her and I'm like, "I know we said 2.5 days, but we have a pilot friend who's flying tomorrow from Italy, and he can bring these extruders way faster than FedEx if you can get it done half a day faster." So then they made that work. Then we said, "Well, how are we going to get these extruders from this factory to the airport?" So we put typical millennial, what do you do when you don't know the answer? You post on Facebook. So we posted on Facebook, like in the Israeli students in Italy group, and we said, "Hi guys, we know this sounds crazy, but we need somebody to go pick up this box of 40 kilos of industrial extruders and to bring it to the airport to our pilot friend who's going to bring this back to Israel for us. Thank you, thank you. If you want to do this, please respond to our message." Again, I'm at Space University all day, so I'm waking up at 5 a.m., 6 a.m. to do this before I go to class at 8. And so I wake up and I see that this girl, Yana, answered my Facebook message that she's willing to go get our extruders. So I'm so excited. So I wake up and I'm texting her, I'm calling her, and she's not answering. Granted, it's 7 a.m. In Italy, and I see I have one mutual friend with her. So I call this guy in Israel. I'm like, "Ro'i, please tell me you have Yana's phone number." So he has her phone number. We call Yana, and that was an awkward conversation. It's like, "Hi, Yana, this is Helen from Facebook. You answered my message. We did the calculations, and you need to leave in the next 20 minutes to get our extruder in time. Can you wake up and go get it, please?" And then she's like, "Oh no, my boyfriend took the car." So he said, Yana could borrow a car, rent a car, take a taxi, just please get us our box of extruders. So Yana convinced her friend that this is going to be a fun trip to go get our box of extruders, and they go to this factory in northern Italy, and then about 2 hours later, I get a phone call, and Yana's like, Helen, I'm really sorry. I have bad news. It hasn't gone through Italian customs yet. They're not going to let you take it out of the country. But don't worry. And customs usually takes 2 days. But don't worry. I'm on my way over there, and I've already faxed them the documents. I'm like, okay, great, thanks, Yana. Meanwhile, we realized we're definitely missing that flight. At this point, I got connected to VP operations of our national airline, and I have a chat with them called Flying to Mars, Smiley Smiley, with him and his secretary. And so I'm like, hey guys, we're gonna miss this flight, but can you put us on the next one? And they said, well, if you don't personally know the pilot, we can't just fly 40 kilos of industrial extruders for you. That's a security risk. Somebody has to get on the plane with this stuff. So then we call back Yana, and we're like, Yana, right? You haven't visited your family in Israel in a while? We'd really like to buy you a ticket. Can you get on the plane tomorrow? So we got Yana a plane ticket, and she came to Israel with our extruders. And then we're printing in Autodesk, which is a big 3D printing company in Israel, and a software CAD company. So they have a printer space. They lent us their printer, and we're printing there. But as we kind of are trying out these extruders and figuring out how it works, we realize it's going to be a 15-hour continuous print. Autodesk closes every day at 6 p.m. So they're like, no, you can't stay here after 6 p.m. We close. And you don't understand. It's a 15-hour print. You can't interrupt it in the middle. And I said, well, can I borrow your printer? And they're like, well, you can't take it out of the building. That would void the insurance. And so then I said, well, if we can't take it out of the building, what if you guys are in this multi-story building, and there happens to be a hotel 3 floors up? What if we rent a hotel room, we take the printer to the hotel, we print overnight, we'll bring it back in the morning, no one will be any smarter. So so that was crazy. We actually were able to convince them of that. So here's the 3D printer in the hotel. It's pretty crazy. That's our friend John Marco is it just barely fit in the elevator. So we're here in the hotel. Again, this is a 5-star hotel. We're here with our buckets of Mars dust, mixing it in the bathroom. It kind of looked like Breaking Bad. And then here's our extruders that came from Italy. They're so nice. And so we had kind of a lot of challenges and sourcing materials. We had some other flights. We flew a box of Mars regolith from Italy that got stuck there with a different pilot friend. Crazy stories. So eventually we were able to print this beam. That was really cool. It did not, unfortunately, perform very well in the NASA testing requirements because it didn't dry. Again, we basically flew it wet from Israel to Boston, where we sent it to a testing facility, and then from Boston to Peoria, Illinois, where we had to submit it. So we paid a testing facility to stay open on the weekend, and we called our pilot friends and we're like, hey, we know you guys already did a ton of favors for us, but we need you to take this beam that's this big and still wet, and we need you to fly it in the cockpit because it's fragile and we don't want it to get broken. So somehow we were able to convince them to do that. That was crazy. So here you can see a little picture of, here, let me jump ahead. You can see the printer working in the hotel. So that was pretty crazy. Can we go to the next slide? Oh, there we go. So this is a multi-year competition. So we did the design phase, then we did the material sample phase. We struggled a little bit there, and now we're working on the subscale habitat. So basically we have 5 deliverables over the next, I want to say 10 months. And the most complex of them is to 3D print a subscale habitat, which is 10.5 square meters. So that's pretty big. And to do that whole thing autonomously. These days we're working on trying to print a foundation, the foundation of the habitat, which is 2 meters by 3 meters. So that's happening this week, hopefully. or this weekend. So these are the kind of the deliverables we're working on for the competition. This is our vision for the design of the habitat. Again, so the idea is to use indigenous materials that are found on Mars for the construction, so that you're not transporting things there, but you would potentially bring like windows and doors and stuff like that, and then integrate those together so you can see kind of the design of the habitat. So about I want to say 4 months ago, Caltech adopted me and Ariel from Israel, and we're working on this project now at Caltech. So they were interested in working on this project, and we basically just started recruiting people at Caltech kind of before we had any jurisdiction there. We just like, hey, robotics team at Caltech, you want to work on this cool project with us? They're like, who are you? But they're like, oh yeah, that sounds exciting. Anyway, so at some point, eventually they officially adopted us at Caltech. Now we belong to the Mechanical Civil Engineering Department at Caltech, and we have some seed funding where we're working on this project. So what we're working on for our foundation concept was actually to have a foldable gantry system that can 3D print the foundation, and the idea with that is that we want to be able to minimize the footprint of the printer so that it makes it more relative for transporting to space. So it actually doesn't fold yet, but it hopefully will print the foundation. So that's what we're working on now. And then for the next phase, for the habitat and the hydrostatic test, our idea, which I think is kind of counterintuitive to what a lot of the other teams are doing, is that we want to print multiple like 3D Lego bricks and then have a mobile robotic arm assemble the Lego bricks. And because the new recipe that we're using now is a mixture of crushed basalt rock with polymer type material, so we're actually able to melt the bricks together to create joints. And so our idea is to have multiple 3D printers printing these Lego bricks and then assemble them autonomously with a robotic arm and then melt them together. So that's what we're going to be working on for the next months. So what's kind of unique about this is if you see kind of other people in the world who are 3D printing houses, generally it's a big system and a small house because the limiting factor is actually the size of the infrastructure in a lot of ways. And so we think by decoupling the printing process and the assembly process that we'll be able to do it in a way that's more mobile and yeah, so that's kind of what we're working on, and we think that strategy gives us an edge as far as the geometry we're able to achieve, as far as system redundancies, and also long-term as far as being able to print in a closed chamber, because the environment on Mars is really harsh, and that can affect the material properties. Even here on Earth, when you're printing, that's one of the issues. If you're doing a print that takes 3 days to print and you have different temperatures, you're going to have different material performances, and it's going to be non-consistent throughout the whole thing. But if you're printing it in closed chambers where you can control the environment and only then you're assembling it. So that's kind of what we're thinking about. It's pretty complicated what we're trying to do, and I tried to sit down and like explain what we're trying to do. That's kind of what I came up with. But hopefully we'll be able to do it. Again, our team at Caltech is amazing. I feel so lucky and so blessed to be there working on this project. It's just a pleasure to work with the technologists there, and it's really exciting and really fun. We also have an architecture partner in Israel, architecture firm. I would say we're still very much lacking in the communications department as far as like telling people what we're doing, social media, websites, stuff like that. It's between like lackluster and non-existent. But it's great that I'm here to share this with you. These are some of our team members. We actually have grown the team more since then. So that's really awesome, and they're all amazing. It's so great to work with them. And then our faculty advisors, the most active ones are Jose Andrade and Chiara Dorayo from the Mechanical Civil Engineering Department at Caltech. Here you can see a couple different design iterations of the bricks as far as like what we're thinking about for the design bricks, and it's kind of a trade-off between the 3D printer and it's a trade-off between the civil engineering properties, how fast you can print it and at what ease you can print it, and then how hard is it going to be to assemble with a robotic arm. So you have kind of a trade-off between all these different things that we're trying to figure out. Here you can see a kind of a design of what we would envision the habitat looking like. But right now we're planning on printing a single dome in April 2019. So hopefully we can figure out some of our technology challenges by then. We also have a couple amazing partners and sponsors who have been helping us with the project. So Webcore Builders, HQ Architects, and Make It, a 3D printing company here in Pasadena. And actually the founders are here. So hi Shelly, hi Salmon. They're awesome. They help us a lot. If people want to come see our 3D, so this is our 3D printer. We're in a garage now in Caltech because we outgrew all of our labs. So they put us in a 2-car garage in a Caltech-owned house. Which is also good because we have to do a drop test on our foundation where we're basically dropping a metal ball from 5 meters height to see how much it cracks the foundation, and you don't have that type of ceiling height in any of the labs. So we're in the garage, it's on wheels, just roll it out and then drop stuff on it. So that's the plan. So this is the frame of the printer. It doesn't have the printer head on it yet. But we're having an open garage, so if you're interested in the project and would like to be involved and would like to come learn more about it, Saturday and Sunday between 5 to 5:30, you're welcome to come to our garage on 287 South Hill Street and to see our printer. I hope it will work by then, but I cannot promise that. I had so much fun working on this project, and I feel so lucky that I get to work on this like insane, crazy thing. I can't believe people pay me. It's like somebody pays me to work on 3D printing Mars habitats. But our team is almost exclusively volunteer. It's mostly students from Caltech, ranging from undergrad all the way through postdoc. But there's other people from industry who would like to be involved with us and involved with the project and are as excited about Mars habitats as I am. I'd love to speak to you. This is my email, and that's the general habitat email. So please feel free to reach out. I hope we actually get to Mars in my lifetime. So thank you.
I think the chances are good. You're young enough. I think that's going to happen. Really exciting. Your passion is palpable. This is just a really interesting story of like when the stars align and everything just seemingly goes your way. I know there's a lot of nuance to that. There's probably a lot of hiccups and bumps in the road, but I think that's just really miraculous in ways how you had this idea and you just all the team members and all the elements just really came together. That's really awesome. We're really grateful and proud of your current success, and we hope you finish this project strong and actually get that project going on Mars. We're going to open up to Q&A now. If you have a question, please raise your hand. John will walk around with the mic. We'll handle questions now, but we're going to take comments and storytelling and all that other stuff later. Helen, will you be hanging out with us for a little bit? So yeah, if you have a story that you'd like to share or about Star Wars or whatever, because I swear that's like, I'm sitting in the back with Alex, and the second that I saw the samples, like the models, I was like, man, that kind of looks like Star Wars. So anyway, really cool stuff. But yeah, please share comments later, questions now. Thanks.
Thank you, Helen. That was actually a really interesting talk. Does anybody have a question? Yeah, one of the things that when I look at these crazy science fiction type ideas and all that is how life imitates art. Did you guys use things like Star Wars, Star Trek, those type of things, and as your inspiration when you came up with some of the ideas for the colony on Mars?
So I'm a little. This on? Yeah. So I'm a little hesitant to actually admit this on tape, but I've never watched Star Wars.
There's the door.
I was like not a space geek growing up. I was like, I kind of just ended up doing this. I got interested in this because I was interested in urbanization and non-populated areas. I was like, well, I could work on building a city like in the middle of the ocean, or on the moon, or on Mars. And then I kind of talked to some space industry people who really influenced me, and they're like, oh, you should do a Mars project. I started reading about it and learning about it more, and they're like, well, actually, that makes a lot of sense. I should. And then things just kind of took off from there. So I didn't grow up kind of like, dreaming I was going to be in the space industry and geeking out on space stuff. I just kind of ended up doing this, to be honest.
In a lot of architecture, I'm sure you're aware, things like bricks or the pieces that you use need to support other things that you build into them. I'm wondering if the people who are doing the structural analysis of your brick design have thought about where within the bricks that you print are you building in places for fasteners, places for small electronics, things like that.
Yeah, absolutely. So at this point, we're very much in an early stage, in the sense that like we're trying to get the printer to work. We're trying to see that we have a mobile robotic arm that can actually like lift bricks and place them together. So that I would say is like very far in the future. Like not worried about fasteners yet. One of the issues though from structural engineering is like, does the structure self-support at each point? Right, because if you're building this in pieces, so you don't have kind of a mold that's supporting it. So you want to make sure that as you lay each brick, it's still self-supporting. So it's not like oh, this could work as a full structure, but when you get to brick 427, the whole thing collapses. And so how we're addressing that with a single structure that we're trying to print is that because it's a dome, you get some support when you finish each circle, right? So the idea is to build it kind of like an igloo in a concentric way, and so then you get a little bit of structural support that way. Still struggling with the capstone and kind of how to deal with that, and I don't think we have a full solution on that. Long term, I think 3D printing is amazing for solving the issues of the fasteners, because you can basically, for the same cost, you can have a much more kind of unique geometry, right? And especially if you're printing small pieces, then you can print the small pieces really in a custom way that have those fasteners and have kind of those cavities prepping for the other components of the house. The other thing that I think is really nice about the bricks is that if one of your bricks is messed up, you can just reprint it and take it out and fix it, versus if you're trying to print the whole habitat at once and it's like a 3-day print and then you mess something up, well, you have to start again, and then what do you do with the house that you just printed? So I think bricks gives an advantage to those types of things.
Okay.
Some projects are evolutionary and some you try to force to the original concept. I'm curious, how much of your original thinking has survived to this stage?
Not a lot. Yeah, very dynamic. We changed. I mean, the stuff that we thought we would do at the beginning of the solar sintering, it's kind of we left that and are doing very different stuff. Another thing, I mean, that's amazing about being here at Caltech and here kind of next to JPL is that you can really talk to people who are actually building stuff that goes to Mars, and so that kind of informs us that as we work on this project and progress, we learn more and more about the industry and more about how people are doing things, and that informs our thinking and changes our strategy very, very much so.
So this may be a stupid question, but I was kind of curious, how do you know so many pilots?
So that's actually a really good question. It's because my co-founder, Ariel, was an officer in the Israeli Air Force for 9 years, and so he has a lot of pilot friends. And also, it's a small country, and so it's really easy and small, highly interconnected, so with a couple phone calls, you can pretty much talk to anyone, so that helps. People are more accessible.
Got another question. The space industry has created a lot of technology that has now become part of our daily lives. And so for what you're trying to create, obviously I think there's also a lot of applications for building homes here on Earth without having to go all the way to Mars. So and you showed some examples of some of the companies that are working on some of those solutions. Are you reaching out to them and looking for ways to collaborate with them? Or is what they're trying to do because of the materials being used and the environment atmosphere just too different from what it is that you're working on as far as Mars is concerned?
So we're actually trying to figure out like what our kind of Earth-based application could be for our technology. One of the things that I suspect it might be relevant for is for disaster relief, specifically for printing infrastructure, because, for instance, when there's a flood and the roads are flooded out, it's really hard to get emergency workers in and to get supplies in to people when they're stranded, and so everything's getting flown in like on helicopters, and it takes a long time to repair the infrastructure. So I think if you could use local materials to print roads, which would enable emergency vehicles to get in faster, I think that that would be a very valuable Earth-based application for the technology. But we're not quite there as far as conceptually, like making sure that there's a market, and also technology-wise, we're not quite there either.
How long does it take to print a brick or to all the bricks in a wall? What's the time?
That's. Yeah, what time does it take to print a brick or all the bricks in a wall? That's an awesome question, and that's, I think, one of the core things that we're working on is how can we minimize the printing time for that? Because I don't know if any of you guys have played with 3D printers at home, but like you put this thing in and it's like this big and it takes like 30 hours till it's done, and it gets stuck in the middle and you have to reprint it 3 times. So I don't know if you've had that experience, but we're trying to create a system that doesn't have that problem. And one of the biggest challenges is like, how do you scale up the printer head? And so the printer nozzle, the printer head that we're working on now is about I want to say an inch. So that's pretty big. Like generally in 3D printers, they're like really small, and ours is like that. And so that creates a whole new set of challenges. Is like, how do you make sure that you have consistent heating through the whole system, and how kind of. Also just like feedstock and material. I mean, we just ordered 2,000 pounds of crushed basalt and like 2,000 pounds of polyethylene. It's like, you don't really kind of, I mean, for me at least, I didn't kind of comprehend like how much material we need to print until it like showed up at our garage in these like huge boxes and got taken off with a forklift. And I was like, wow. So those that's definitely a challenge. One of the other ways that we're working on addressing this is some research that my colleague Ariel had worked on previously was like a multi-resolution nozzle. So basically, you can print with different size nozzles. So it kind of rotates. I almost think of it like cake making kit where you like switch out the tips to get like different frosting geometries. So think of it kind of like that, but just that it automatically rotates, and so then you can print more accurate geometries. Like this is very much on kind of the conceptual level. He applied it with different materials and a different scale, but basically where you have places where it's important to have an accurate geometry, like where the bricks are intersecting and you want to have a tight fit, then you can use a smaller nozzle, and then places where you just want to like print stuff fast, you could have a bigger nozzle. So that's something we would look at into implementing long term.
Over here, Helen.
Yeah.
Hello. I have a pal in Orange County, and he worked with Buckminster Fuller for a couple of decades. To what extent have you looked at his history and drawings early on for the geodesic dome design?
So I think the geodesic dome is an amazing structure. I'm a big fan, and I think that there's a lot to learn from that. I think our design has been informed a lot from a lot of architectural history as far as what's been done up until now. We're also very inspired by Romanesque architecture because, and it's kind of interesting to take kind of this very old traditional architecture and try and kind of implement it in new technologies. And kind of what inspired us from the Romanesque architecture was really kind of the building methodology and having these like very thick walls that are self-supporting, which is relevant again to here, because if you're not using kind of internal scaffolding or supports, then how are you building that? Plus, one of the other things is that on Mars, probably there would be very thick walls for radiation protection, and that also is something that's in common with the Romanesque architecture style. Yeah.
Hi, so early on, one of your cartoons showed a robot running around sintering bricks, and then we morphed into wet stuff that has to harden. How far along is your sintering technology, if at all?
Yeah, so the sintering was our initial proposal for the like the design phase. And we said, yeah, we think we can sinter it. And then we got to phase 2, and we saw the scoring chart for NASA as far as like what materials they would be interested in for 3D printing. And so that kind of guided the rest of our development as far as what materials they find relevant for 3D printing. One of the problems with sintering is that it's very energy intensive, which makes it maybe less relevant in some ways. And so we very much abandoned the sintering, I would say, before we even started in some ways. Kind of we had the conceptual idea of sintering, and then when we got to the material phase, we kind of shifted very, very significantly to doing something else.
But ultimately, that's what you'd need on Mars.
So the material that we're using now, it's the crushed basalt mixed with polyethylene, and then the thought about using polyethylene is that it's a recyclable material, and my understanding is that NASA would have 200 to 300 kilos of polyethylene on a mission to Mars that could be recycled, and it has good radiation properties as well, polyethylene, and so that's essentially like the glue that we're mixing with the crushed basalt, and the crushed basalt is simulating local Mars material. So the idea is to use local materials as much as possible. Yeah.
Yeah, we got time for one more question. Here we go. Yeah, you're welcome.
How do you envision climate control within the habitat and pressurization? How are you going to accomplish that?
That's a great question. That's something that I think pressurization is something that we're still very much struggling with and trying to figure out, especially with the bricks. I think it does well with external pressure, not as well with internal pressure. And so we're trying to create a brick geometry that's going to lend itself better to supporting the internal pressure from the habitat. But yeah, I would say that's something that we're still very much actively looking into and trying to solve. If you have any good ideas for that, we'd love to talk after. But we're at this point very much guided from the different deliverables of the NASA competition, and it's kind of interesting the way they structure it in that each phase they kind of add like more components, right? So like for now, we're not asked to solve like the radiation component. We're not asked to solve internal pressure. We're working on, can we do this autonomously? How autonomous is it? How fast can you print? Does your material do well with thermocycling tests and compression tests? And kind of as we progress in the stages of the competition, we have kind of more and more tests that we're sending to, right? In 2016, we just did the compression test. Now we're doing thermocycling tests. In 6 months, we're going to have a smoke test. So we're kind of, as we progress in the competition, we're kind of developing more robust solutions.
Excellent. Thank you so much for the questions, guys. Expert mode. Wow.